proving identities. This tends to be a section students struggle with, and I'm never really sure why. And what I mean by that is in previous sections, I've given you trig expressions, and I've asked you to simplify them. And usually students are okay with that. And the only difference between a trig expression and a trig identity is when I give you identity, I'm telling you what the answer should be. Where when I just ask you to simplify, you have to kind of figure out what the answer should be. And let me show you what I mean by that. Here's an example. Cosine to the fourth x minus sine to the fourth x. I'm pretty sure this was a problem in one of our previous sections. And the directions were to simplify that. Well, now I'm going to tell you that when you get all done, the answer should be 2x. So what I'm really saying is take cosine to the fourth x minus sine to the fourth x and simplify it. And when you get done, your answer should be cosine 2x. So I'm giving you the final answer. You just have to do the work in between. All right, so the way these identity goes is you can work with one side at a time. So you pick one side or the other. Traditionally, you kind of start with the side that looks a little bit more complicated. So if I were doing this identity, I would start with the left-hand side, cosine to the fourth x minus sine to the fourth x. And what I would notice is that the factors, this is cosine squared x plus sine squared x times cosine squared x minus sine squared x. So this problem might have actually shown up in a couple different sections. It might have shown up as one, just to simplify by factoring, and two, it might have shown up in another section, just to reduce it. All right, well, now here's where we start using our famous identities. Our most famous identity is cosine squared x plus sine squared x. That's the Pythagorean identity. That's 1. And then cosine squared x minus sine squared x, that's one that you might recognize. That's one of the forms of the double angle identity for cosine. So that turns out to be cosine 2x. And we're done. We get cosine 2x. There's our final answer. All right, let me grab another one here. How about 1 minus cosine x over sine x equals sine x over 1 plus cosine x. This is actually another famous identity you might recognize. This was our tangent x over 2 identity. And I claimed that those two things were equal, but we didn't prove it. And now we're actually going to go ahead and prove it. Now, here's the mistake I will see an awful lot of students make. The mistake I'll see students make is they have this equation, which they're trying to prove is true, and they'll kind of assume it's true. And what students will do here is they'll cross multiply. Well, you really can't do that. Because if you cross multiply, the property of cross multiplying assumes that those two expressions are already equal. The only time cross multiplying works is when you know they're equal. We're trying to prove they're equal. So when you work with an identity, you have to start with one side and one side only, and work with that side. You can do a bunch of steps to that side. If you get stuck, you can then go to the other side and do a bunch of steps and try to get it so that the two things are equal in the middle. That's fine. But you can never do the things we do in algebra. And what I mean by that is you can never cross multiply. You can never add to both sides of the equation. You can't multiply both sides of the equation by something, because then you're assuming it's a true equation. All right, so what would we do? Well, for this problem, we pick one side or the other. Just to be different, I'm going to pick the right-hand side. And the reason I picked the right-hand side is the right-hand side looks slightly more complicated to me. To me, it's more confusing when I have multiple things on bottom, and the bottom for this one has 1 plus cosine x. So I think the bottom's a little bit more confusing. That's why I'm picking this one. All right, now here's a standard technique. Whenever you see a 1 plus cosine x, or a 1 minus cosine x, or a 1 plus sine x, or a 1 minus sine x, what you should be thinking of is the Pythagorean identity. To make the Pythagorean identity show up, I multiply by the reciprocal. So I see that 1 plus cosine x, I'm going to multiply by 1 minus cosine x. And the reason I do that is when I do FOIL on bottom, I get 1 minus cosine squared x, which fits into our Pythagorean identity. Now on top, I'm not going to distribute through. I'm just going to leave it at sine x times 1 minus cosine x. In general, on these problems, distributing is a bad idea. And looking ahead a little bit, I see that when I get all done, I really want a 1 minus cosine x, so I guess I'd like to just leave that 1 minus cosine x there. I don't want to complicate it. All right, well, we're almost done. Now we have sine x times 1 minus cosine x. We purposely set this up so we could use the Pythagorean identity. 1 minus cosine squared is sine squared. And then I can reduce. I can cancel a sine x on top with a sine x on bottom. And I think I'm all done. I have 1 minus cosine x over sine x, which is the other side, which is exactly what I wanted. All right, let me do a couple more problems here. How about this one? Tangent x plus cotangent x divided by secant x plus cosecant x is supposed to equal 1 over cosine x plus sine x. All right, well, where to begin on this one? Well, I look at my two sides. Which side looks more complicated? I hope you would agree with me that the left-hand side looks more complicated, so I'm going to start with my left-hand side. So I'm going to write tangent x plus cotangent x over secant x plus cosecant x. All right, well, I notice when I get all done, I want things to have sines and cosines in them. So this is, again, a very standard technique. When you have tangents and cotangents and secants and cosecants, a very standard technique is to turn everything into sines and cosines. So I'm going to write tangent x as sine x over cosine x, plus cotangent x is cosine x over sine x, divided by secant x is 1 over cosine x, and then cosecant x is 1 over sine x. Okay, very standard technique. When you have the I consider them kind of the off trig functions, not sine and cosine. Turn everything into sine and cosine and then see what happens. All right, now I have what's called a complex fraction. So what I would do is I would make it not so complex. I'm going to take this fraction and I'm going to multiply every term by cosine x times sine x. Why do I pick cosine x times sine x? Because that's the common denominator. I looked at my 4 fractions. That's my denominator. All right, so I'm going to write this all out. It's going to be pretty big, but I think it's going to simplify down nicely. So I'm going to have sine x over cosine x. And I'm going to multiply that by cosine x times sine x. Plus cosine x over sine x. And I'm going to multiply that by cosine x times sine x. And then I do the same thing on bottom. I have 1 over cosine x times cosine x sine x. Plus, finally, 1 over sine x times cosine x sine x. Now, the whole reason for multiplying by my common denominator is going to make a lot of fractions go away. So what I mean by that is those cosines reduce. So I'm left with sine squared x right there. Those sines reduce. I'm left with cosine squared x right there. Here the cosines reduce. I got a sine x. And finally, the sine x is reduced. I have a cosine x. And now, look what happens. It just fell right out for us. Sine squared plus cosine squared, that's 1. That's our Pythagorean identity. We have sine x plus cosine x on bottom. But of course, sine x plus cosine x is the same as sine x, or cosine x plus sine x. We can simply switch the order there. Okay? So that gives you the basics of proven identities. The things to always look for the Pythagorean identity. That's the one you use almost all the time on almost all of these problems. So look for your conjugate pairs. If you have a 1 plus a cosine x, you typically want to multiply by a 1 minus cosine x. And then for the other problems, if you have secants and tangents and such, generally you convert everything to sines and cosines, clear your fractions, the Pythagorean identity usually shows up, and it works out.